Okay, so we had 3 lectures on duality theory and KKT conditions, and I want to give a kind of bird's eye view of what happened and why, and what tools we have available, and how this is going to look like when it gets applied in your research. As always, just interrupt me if you have any questions. So the core idea in duality is that given any optimization problem that we tend to call the primal problem, we can construct a second problem that's equivalent in some sense, that's a different perspective on our original one. And the second problem is called the dual problem. So given in most generic form, min over x of x that has constraints, inequality constraints, and equality constraints, we can always construct from this primal problem a dual problem, which is a maximization problem over variables u and v, with the only constraint that u is greater than or equal to 0. And there's a standard way to construct such a dual problem. And there are many advantages that can be had from doing that. So we went through a number of different advantages. So the first thing is that the relation between these two, these are in some sense equivalent. In the most general case, when f is not necessarily convex, the minimum of this problem is always greater than the maximum of this problem. So if f star is the minimum of the primal and g star is the maximum of the dual, we always know that f star is greater than or equal to g star. And stronger, we know that if we have a convex optimization problem, which is the most common case we deal with, then under very weak conditions, Slater's conditions, we actually have that f star equal to g star. So given that we have this, there are many things we can gain from going to duality. The most obvious thing is the dual might be simpler to solve than the primal. So we can already see that the dual only has this very simple inequality constraint. Depending on how G looks like, this might be a much easier problem to solve than this. The other advantage of going to duality theory is that even if this is not convex, this problem, we've shown in class, and we're going to really quickly review why, is concave. So you're maximizing over a concave function. We're no longer guaranteed that what you're getting is the result of your original one, but if it's very close, and you couldn't solve this one at all, but you can solve this one, then we've gained a huge advantage. So we're saying that the dual might be easier to solve, and we said that this tends to be easier because of the constraints getting much easier. And sometimes we can even solve the dual in closed form or through some very, very simple algorithm. It might be faster to solve. So if this one, if x was in R to the n, and n could have been very, very big, but we only had a small number of constraints, u and v, their dimensionality will be equal to the number of constraints. So if you had like a million data points here, but only 10 constraints, you would get a 10-dimensionality problem, which can be much, much easier to solve. So those are the two obvious things. And then the less obvious things that we use all the time, and you've already seen in class with the lasso, and you're going to see in the homework again, is that we can get insights by just looking at this problem. Like seeing what kind of solution. For the lasso, it's very, very interesting. You'll see in the homework that just staring at what formula you get here tells you that the solution of the lasso is stable, in the sense that when you're trying to find a sparse solution for a problem and you perturb that problem with a small amount of noise, the new solution you get has the same sparsity pattern. That's completely not obvious anywhere from here, but from basic geometric intuition here, you can find that out. So just having this alternative point of view can give you new insights. And like the last thing is, maybe these two are equally easy or hard to solve. Let's say like medium hardness, you can do something about it. Well, if you start solving both of them at the same time, these two values, as you're estimating them, should get closer to each other. So you can bound how far you are from the result by how quickly these get close to each other. And that's a stopping criteria for an algorithm. So all I'm arguing here is that having two perspectives is good for many, many purposes. And and what I didn't say here about new insights is also we'll get new insights from the KKT conditions as well. And once we have buy-in into why this might be useful, we're going to see like there's so many research papers. They all do that. They'll be like, oh, here's a problem. This looks hard. We compute the dual. This looks easy. Let's do it. So then the next obvious thing is, who's this magic dual? What's going on? And as we saw in class, the key idea is to create approximations like lower bounds to f that we know how to solve by getting rid of the constraints. So the key idea there is that if you're given f and you know you have these constraints, then you can add these constraints to the objective. And you know that if you add a positive multiple of this constraint, well, you're going to only get something smaller because this is negative. And if you add a multiple of this constraint, you're not going to be doing anything because this is 0. So we construct what's called a Lagrangian. That's the first step of getting the dual. Let's say it like this. And I'm not going to go in detail over all the derivations again. Hopefully this is just a reminder that we've argued that this is more than equal to 0 on the constraint set. This is 0. So this is smaller than equal to f on the constraint set. And from here, all we said is, OK, well, we have a lower bound on the constraint set. We're still under constraints. That's kind of upsetting. But we know that, we know that if we have a lower bound on the constraint set, if we get rid of the constraints, we're going to get an even lower bound. So we argue that this is more than equal to min over x in general. And we just gave this guy a name. This guy is now a variable, a function of only u and v because we've eliminated x. We've chosen a particular x. So we just call this the dual function. So we said, the dual function everywhere is an underestimate. So why don't we just take the best underestimate, the best lower bound? So we said that this is in particular greater than or equal to max of g over u and v, which was just defined to be g prime. So whenever we have an optimization problem, in order to derive the dual, we just do the following steps. Step 1, we write the Lagrangian. Step 2, we compute the minimal of the Lagrangian, and we call it g. And then we just write our optimization problem. We now have a g, so our optimization problem is this guy. Okay? So you've already seen, how many of you did from the homework exercise 4, the one that asked you to compute a dual? Did you do exercise 5 or did you just not do the homework? Okay, who did exercise 5? I want some participation here. Again, nobody did exercise 4? Well, then let's compute a dual. So in general, how comfortable are you comfortable computing duals? Say again? Yeah, so let's do a simple example. Just to see that these steps, just do one of them at a time, and you're going to get the result out the other side. What problem shall I take? Okay, so one of the problems that is actually from your textbook, which is a fantastic textbook, and I hope you guys are reading it, because it's one of the best textbooks I've ever seen. It's the problem of entropy maximization. So let's do this. So you're trying to minimize xi log xi. This is just the negative entropy, subject to inequality constraints on x and an equality constraint. It's just saying that x is a probability distribution. Okay, so if we didn't know duality theory, would we know what to do about this? Do we have any method for approaching this if we don't know duality theory? Say again? That's duality theory. But like, what did we learn before that? Exactly. So the only thing we could possibly try is projected gradient descent. So first of all, this is a projection over a probability simplex, which we didn't even talk about, was not trivial. And this is a projection over a general polyhedron, which we already mentioned in class that there's no general, it's very, very hard. So like if all we had was first order and second order methods, we're screwed. We don't know what to do about it. And that's on camera, great. So let's start duality theory. So how do I compute the dual of that problem? Can people just tell me what I'm supposed to be doing? Step one. Right, so what am I writing? So just literally this problem. Can you write, what's the Lagrangian of x, u, and v? Okay. Then? Ax minus b, v transpose minus 1. Okay, so I wrote the Lagrangian, great. What do I know about u and v? Only u's bigger than 0, right? Because we don't care about this one. This one is supposed to be 0, so you can have whatever. But this one's supposed to be negative, and you're trying to get an underestimate. So this one should be smaller than 0. Okay, so I wrote the Lagrangian. Go for it. Oh, yeah, you're right. Sorry, out of habit. V is a number. Cool. Okay. What next? Right. So I want to minimize over x. How do I go about it? Great. Okay. So I'm going to try and take the gradient. I'm going to take it component-wise because this looks too messy for me. So I'm going to just look at an xi. So the d over dxi of this guy. Well, let's see all the terms for this. So from here, this is a product. So I get log xi plus xi times 1 over xi, so plus 1. What do I get from here? Say again? Yes. Well, almost. It would be the transpose of that, because if you do u transpose, no, you're right. That's fine. I take that back. My mistake. Okay. And then what else? Good. Awesome. Plus v. So I take this, and I set it to 0, right, because I'm trying to minimize. And I get that xi is e to the minus U transpose AI minus V minus 1. Okay. So I got my minimizers. What next? Exactly. So, sorry. So I'm getting G of UV is plugging this back in. I'm not going to run through every single detail of the calculation because it's not that important, but just like looking at what's going on. So if I plug this xi in here, I'm getting minus U transpose AI minus V minus 1 from the log times xi. I'm going to leave xi for now, this one untouched, this one substituted, because that turns out to be easier, plus, so this is a sum over I. Xi plus, so I've taken this term minus U transpose V, sum over I, Vi xi minus V. So I've just been like lazy about where I substitute back and not, just to underline that this term in here simplifies with this term. This term simplifies with this term. And what we get is minus sum of xi. So now I'm going to plug that back in. So minus sum of E minus U transpose AI minus V minus 1 plus some other terms, minus U transpose B minus V. Yeah, that is what I get. So what do I have now? I started from this optimization problem that I had no idea how to solve. Literally no method, and now I have max over U and V with U greater than or equal to 0 of this thing, of minus U transpose B minus V minus some sum of exponentials of something simple. What do I do about that now that I have a dual problem? Do we know how to solve that? How do we solve that? Somebody else besides you guys too. Say again? Yeah, we can do gradient descent, and we have this constraint, but we know how to project on that. We'll take a U, and all the negative components will make 0. We'll do projected gradient descent. And this is trivial, and this is concave, and nice, and well-behaved, and smooth, and like everything we could possibly ever want. And we know that this is convex, the minus entropy is convex. So this is a convex optimization problem, so we have strong duality. So we solve this guy, which is trivial, and we get the solution to that guy, which is totally not trivial. So this is what this looks like, the best case scenario when duality gets applied in practice. You run 6 lines of calculations, and you turn an impossible problem into a trivial problem. So that hopefully is persuasive, because that's persuasive for me. So when you use this in research, you do the exact same things, but the formulas tend to be a bit more complicated. So people have come up with a lot of like tools to deal with problems that are just messier. And one of the most common tools we have is conjugate functions. You know how that definition looks totally like arbitrary, and why does it even have a name? It's because it appears in this all the time. So I think conjugate functions actually have a motivation from outside optimization, which I don't know. I don't think they're just dependent on us. But from our perspective, motivating the definition of conjugate functions is trivial. So I'm just going to put the definition up there. So given a function f, its conjugate f star is the following formula. The maximum over x of y transpose x minus f of x. And there's a geometric interpretation, and we saw that in class, and you can look at it in lectures again as a way to remind you of what this looks like. But the reason we care about it is the following. If we write any optimization problem with linear constraints, which is very, very common, so if we write min of f of x subject to ax equal b, then let's see, like, what happens when we try to solve this, the most common way, right? Let's go again through the Lagrangian. So what am I writing here? L of x and v, we don't have a u because we don't have inequalities, is simply f of x plus v transpose b minus ax, right? And we're trying to minimize this. So I'm just going to write g of v is min over x of this, and I'm going to rearrange it a bit. So, well, I'll rearrange it next time. So this is equal to v transpose b, because this term doesn't have an x in it, plus min over x of f of x minus a transpose v x. Yep. There you go. So all I did was take this term in front, bundle up everybody who had an x, and reorganize that. And then we know that min of a function is minus max of minus the function, right? So then all you get is v transpose b minus max over x transpose x minus f of x. And you can think of this as some vector y. And if you think of this as some vector y, then this is just the definition of the conjugate function. So this is just v transpose b minus f conjugate at y. So f conjugate at a transpose v. So wherever conjugate functions were invented for, they're like the most common thing that happens in, well, maybe I'm exaggerating, a very common thing that happens when you take duals. So then what people do is they learn a bunch of conjugate functions, and they learn a bunch of rules about how to take conjugates of something slightly messy. So if you go on Wikipedia, there's a big table that I'm not going to bore you with that says stuff like the conjugate of a function of ax, the conjugate of this entire thing, is the conjugate of f computed at x over a. And all of these have trivial proofs that you can go through, and you don't even need to remember them. But when you have an ugly conjugation to take, you're like, oh, this is a composition of this and that. Let's go check what's its conjugate. So you make everything modular and simple. And this saves you a lot of pain. Like whenever you think you're stuck and you get lost in a calculation, remember to modularize. And the critical one we learned, the conjugate function that is super useful for optimization, is conjugates of norms. We know exactly what is the conjugate of any norm. And we went over that. So we said that if f is a norm, then the conjugate of f it's the conjugate at y, is just going to be, this is the set, what do we call it, not identity function. I can't remember the word right now. The function that's 0 on the set, the support function, that's 0 on the set and infinity outside the set. So this thing will be 0 if the dual norm, this is the dual norm of y is more than or equal to 1, and infinity otherwise. Okay? And we've already seen this applied. Where'd you guys see this already? Okay. Anything more specific than in the lecture? When we're doing the lasso is regularized with norm L1. So then we got a term on the other side that came from the conjugate of the L1 norm that looked like this for the dual norm. What's the dual norm of L1? Exactly. So if you remember, you don't remember it enough. I'm going to go through the example. So here's really quickly what's going on. So let's say, for example, let's do something simpler than a lasso. Let's say we're just trying to minimize the L1 norm of x subject to ax equal b. This is not what we're doing in the lasso, but this is a very trivial example to look at what happens when you put the L1 norm in. Really quickly, let's see, what do I do again? So I write the Lagrangian, which is this minus u transpose b minus ax. Okay. Then what do I do? Plus. Sorry. So then I'm going to want to take the minimization, but instead of like redoing a lot of work, I'm going to rearrange this. So I'm going to say that G of u is u transpose b plus min over x of the one norm minus a transpose u transpose x. So I just rearranged exactly in the style that I saw was helpful and useful over here, right? And then I do the exact same trick. So I'm going to switch them into a max. I'm going to switch this to a minus. I'm going to switch these terms between them. What do I get? Well, exactly. So this is equal to u transpose b minus it's probably right, but I can't hear it, so it doesn't count. So this is our f, right? So this is minus f star over here. So who's the conjugate of the one norm? Exactly. So I'm going to have a shorthand here. This is going to be the indicator that A transpose U in infinity norm is more than equal to 1. I hate this notation is very verbose. This is cheating, but this is what it's saying. Okay? So I didn't need to rederive anything fancy, like take, differentials again and solve for whatever and so on. This is just a plugin. And this keeps generalizing. So like, here, let's do another one. Can I sneak this in? Well, so let's say I'm trying to minimize the trace norm of a matrix subject to a linear constraint on the matrix. You know how normally, if we're trying to put a linear constraint, say just one of them, we would say A transpose X equal B, right? Like this is just putting n of them in parallel. This would be only one. What's the equivalent of a linear constraint, like something that looks like this, a dot product in matrix world? We saw this, you guys saw this in homework in E-phase painful exercise on subdifferentials of matrices. What was the concept of a dot product in the matrix world? Yeah. So this is one linear constraint on X, okay? So this looks like a really painful problem. Let's do the same trick to it again. So let's write the Lagrangian, okay? What's the Lagrangian? Trace norm of X plus U B minus trace, right? And skipping a few steps, we know that G of U will be UB minus the max over x of the same thing as always, right? This trace minus x. So what will this be? Okay, maybe let's be more explicit. X minus, right? So who's this max? So it's the indicator that the dual norm of this guy. So the dual norm of the trace norm, remember from the same payful exercise, is the operator norm, right? So this is just the operator norm equal to 1. So again, like we didn't need to rederive anything complicated. Given arbitrary, ugly, annoying norm, just do this, get the other arbitrary, ugly, annoying norm instead, okay? Oh, yeah, exactly. Sorry. Yeah, and that was actually critical because I wanted to make another point. So let's look even in more detail at this, okay? So I need more space than this. What am I going to delete? You guys saw this enough times. So let's see what we gained by doing this. So we started with minimize. Oh, I'm sorry, guys. I'm sorry. I'm hurrying up. You're right. There you go. Thank you for your patience. I'll stop hurrying up. OK, so we get this, right? Let's see what this has bought us, because we went from one thing to another equally complicated looking thing. Well, so let's write our optimization problem. So this is max over u of ub minus ua. OK, so the first comment I'm going to make is, what's the dimensionality of u? Yeah. So even if we didn't know anything else yet, this is a good sign. But even simpler than this, the standard way to rewrite this is really as a constraint problem again. We got this an indicator function. Indicator functions aren't very nice. We tend to rewrite this as a constraint problem, right? So what's this? This is equivalent to max of ub subject to what? Say again? Yeah. Does this make sense to people? Yeah. Now, how hard is this? Much, much easier than that. Remember, u is, so a is given, a is fixed, right? And u is a number. So we can just take u, so we can say, this is operator, let's not forget. We know that you can take out constants from any norm. You don't care what norm it is. It's more than equal to 1. So you can rewrite this as u is more than equal to 1 over the first singular value of a. Oh, that's where you were getting with take. Sorry, you actually meant compute. Sorry. Yeah, you're right. Exactly. So I know what u can be max, and now depending on the sign of b, like if b is positive, then the maximal value here will be b over sigma 1 of a. And if b is negative, sorry, well, yeah. Yeah, that's actually it. The maximum value in both cases is b over sigma 1 of a. And the optimal u is sine of b divided by that. So we again took a problem that we had no clue how to solve, and we didn't even need to optimize it. We solved it in like closed form. And obviously we didn't get the x out of it, we only got the optimal value. So if we also needed the x, then we'll see that we can do that with the KKT conditions. But this is a start, okay? How are we doing on time? Went through this, went through this. Okay. So before I move on, are there any questions on the dual problem and Lagrangians and so on? Because they're going to be on the next homework, so this is your last chance before the homework hits you. Okay, awesome. So let's keep doing this. Just for the record, we saw this a bunch of times. And we kind of saw this in terms of you get like from an n-variate to a univariate. We didn't see this that much, but this will be on the homework, and this just comes up when you implement it. So we already covered. So the next way to get insights and to get powerful results is the KKT conditions. So when we did, I'm really sorry I erased it. When we did the entire derivation on why you get weak and strong duality, why do you get that the optimal of G is smaller than the optimal of F, we had a bunch of inequalities there. All the big deal about KKT conditions is if you have strong duality, you know that all those inequalities are equalities. And if all those inequalities are equalities, then they have to hold. So the KKT conditions are what has to happen for those things to be equalities. That's where they come from. And so the KKT conditions, hopefully you're familiar with them by now, are stationarity. So what stationarity says is that once we solve the dual problem and we got U star and V star, we can get X as the minimum. X minimizes the Lagrangian. At U star and V star. And this is written usually, obviously, with subdifferentials as 0 is in the subdifferential X. This is a star. L. Okay. So that's what we see usually. And then the second one is complementary slackness. So all the complementary slackness is saying is, well, one of the approximations we made was to subtract something smaller than equal to 0. If we want that to not be an approximation, that thing better be 0. So for that thing to be 0, all you have to have is that ui star hi at x star has to be 0 for all I. And then we have primal and dual feasibility because, by definition, if they're solutions, they should be primal plus dual. So, and yeah. Okay. So there are many ways to use the KKT conditions, many different ways. The first obvious one is if they look manageable, just solve them. for like, assuming you don't know either x, u, or v. Solve them, you get a solution x, u, v, and that's guaranteed to be both your primal and your dual solution. And you saw this, do you remember where you saw this? Because we did that once. We did that for the problem of 1 over 2 in class. So this looks like a problem that normally would probably do some projected something to it, right? Because of the constraints, you don't expect to have a closed form solution. But we did this in class, and if you don't remember it, I'm going to do it again because it's really quickly. All we did was take write the KKT conditions, right? So it's, what's the differential of f? Okay. So this is differential of f. We don't have inequality constraints, and we have an equality constraint. So from the equality constraint, what do we get? So I'm trying to calculate this. So I already added this. This term doesn't exist, and then there's this one left. Yeah. But we're trying to be in column space, so A, B. Okay, so what does stationarity tell us? So this is the derivative of L. So stationarity tells us that this is equal to 0. Okay, what does complementary slackness tell us? Nothing, okay. What do primal and dual feasibility tell us? Yep. So these are the KKT conditions for this. And we saw that you can think of this as something multiplied with xv equal to something else. So this is in block matrix notation, QA. I'm getting some transposes wrong here. Yeah, I think you are right. Yeah. 0 xv is minus c0. Okay, don't hold me to this. There might be some minor errors. But this is the main idea. Like, we had something that looked like it needed an algorithm. We wrote the KKT conditions. They ended up being multi-matrix operations. We just take the inverse of this guy, and we get both the primal and the dual solutions out of them without an algorithm. So this is an example of where just solve the KKT conditions gives you the solution. And in all honesty, this doesn't usually happen. Like, that's kind of a simple example. But you can still write the KKT conditions and see what they tell you. They will tell you all sorts of stuff. So that's the first use of the KKT conditions. What do you envision might be a second use of the KKT conditions? Or something you've seen, or? Simplify the? That's true. That's true. So the KKT conditions are going to connect the x's, the u's, and v's. So you can keep transferring stuff from one to the other. Like if you know something in one side, you can try to bring it to the dual. Or if you know the dual, try to bring it to the primal. Yes. So we usually call that characterizing the solutions or like whatever. What's something else we can do? Especially look at that stationarity condition. Exactly as it's written, x minimizes L x star, sorry, Lx u star v star. You can solve the dual. If you can solve the dual like we showed, that they're primals, you can solve the duals you can't. Plug u star and v star in the Lagrange, and now to get x, you solve an unconstrained minimization problem. So you know how we were saying, oh, okay, great, you can solve the dual, but you only get the value f star, you don't get x star. Well, this is a way to get x star now. So the algorithm is take primal, write the dual, solve the dual, get u star and v star, the dual solutions, plug them back into the Lagrangian, and solve for x star. And we can do this right here. So in this problem we were writing, I don't want to write all the steps out, but we got a closed form solution for u. So we can plug u back into this Lagrangian, and this Lagrangian is now a function only of x. It no longer is a function of u because we plugged the optimal u. And it's still an ugly function, but we can do it's unconstrained, so we can do subgradient descent on it or whatever we want, generalized gradient descent. So again, for something that we had no solution for, not just that we found out the optimal value through the dual, but we came back and found out the optimal primal value. So this is the third way KKT conditions come into play. Okay? Cool. So that's kind of everything we covered in class. I want to go really quickly through a comment that was in the slides but wasn't made in class, which was the following. When you write optimization problems, like you actually want to optimize something in the real world, you usually don't quite have all the information you need to write this. So a very common thing is to say, oh, I know I want to minimize an objective f of x subject to some constraint on another function h being small. Small is not particularly informative, so usually write being smaller than, say, a value t, and t is something that you guess. You try a bunch of values and you do cross-validation, like you try a grid of t values, right? So t is a tuning parameter. And people write this, and they say then that that's the exact same thing. So this is the constraint form. And this is the form that comes up naturally in problems. This is how we see it when we write, our robotics problem. And then they say, oh, this is exactly the same as the Lagrange form. And the Lagrange form is min f of x plus lambda h of x for some other tuning parameter lambda that they treat exactly the same. Like instead of tuning this guy via cross-validation, they tune that guy via cross-validation. And I don't want to go through all the tiny details in the slides. What it says in the slides is that essentially if the constraint is strictly feasible, these are perfectly equivalent. And if it's not strictly feasible, then they're almost equivalent. They might be slightly not equivalent. But for all points and purposes, like the strict feasibility requirement is a very, very loose requirement. So you will see this written. And why are these two equivalent? Well, the reason they're equivalent is that what you would do is the following. You would start from this, if you were going to be all proper, you would start from this problem. You would write the Lagrangian. You would obtain the dual. And if this was feasible and convex and everything nice, we knew that if there's a primal solution, then there's a dual solution. The dual solution is equal to a primal solution. We knew all these things guaranteed. So we would know that there exists a dual solution, lambda star, which was associated with our t. So for any t we gave it, we would obtain a dual solution lambda t, right? And then when we apply KKT, we would go with stationarity, and we would say that x minimizes the Lagrangian for the lambda equal to the thing that we got by solving the dual, right? So that would be the proper way to do it. But given that t is something that we try everything and we find the best guy, there's a direct correspondence between these two. So it's exactly the same as saying, well, let's just try all lambdas. Instead of going through horrible pains, if we're going to try all t's, we're going to directly try all lambdas. And that's also guaranteed to give us the same best solution. So this is like slightly cheating because, as I was saying, if the constraint set, blah, blah, it might not be the same, but it's such a common thing you see in all the papers taken for granted that you should be aware of it. And if you want to see exactly the arguments for when it doesn't hold, it's in the slides in the KKT lecture. Okay? Do I still have the room for some more time, Ife? I want to go through one more thing. How long can I go over time?
6, 5.
Okay. So has any of you looked in Boyd at the geometric interpretation of the dual problem? Because I thought that was like mind-blowing. Has anybody seen it? Like this picture? Okay. Quick overview. And you can go through the details to look at it later, but I thought this was so cool. And that it finally made like some sense. Here's what's going on with the primal and the dual. And this is just one of many interpretations. If you read Boyd, it's got a whole chapter on the different interpretations of the dual. But here's a way to think about it. So we have our problem. And let's try to build a geometric view of it. So consider any single x associates with a point in a big multidimensional space, which is f of x. Let's call this t, so we go faster. And the value of all of these functions computed at x. So hi's of x and lj's of x. And let's give these some names. I'm out of inspiration because the notation is not good. So let's say these are a's and b's. This is very bad notation. No, let's just call these h's. Let's overload and l's, but at least we'll remember where they come from, okay? So this is a point in, this is one-dimensional, this is however many inequality constraints we had, and this is however many equality constraints we had. Okay, so if we take all if we take all such points, we're going to span all, a space of this dimensionality. But you can also talk about what is the feasible space in terms of when we're satisfying the constraints, all these h's have to be smaller than or equal to 0, and all these l's have to be 0. And you can think of this as what we're trying to achieve is to solve this optimization problem, f star is the minimum t, the minimum of this component, such that THL is in the set of all the guys spanned by all the x's. So if we call this whole set G, this point was in G, and such that H is more than or equal to 0 and L is 0. Does this setup make sense? So we just said take all the x's, you're going to generate a mini multidimensional set. The what? Say again? Oh yeah, sorry, exactly. Good. Yeah. So take an x, span a big space, say that the feasible part of it is the part that satisfies these constraints about the points in the space, and you get a set called G, with these two conditions, and F is the best one. So if you try to draw an image in very low dimensional space, so say that you have one inequality constraint, so this is dimensionally 1, and no equality constraints. So we're going to have a two-dimensional space, T times H, and we're going to have an arbitrarily shaped G. Especially if F is not guaranteed to be convex, this set could have whatever shape it wanted. So I'm going to draw a wobbly G over here. Here's a G. And let's picture, what did we say we're trying to achieve? We're trying to find the minimum T in the part of G that satisfies H being smaller than 0. So we're trying to find the minimal T in this part of the space we can reach. Who's the minimal T in this part? This dude, exactly. So we're trying to find this point, okay? So here's how dual methods approach it. It sounds very counterintuitive, but what dual methods are doing is that they draw, they're essentially building like a convex hull around this G, focused on this area. So focused, do you remember from when we did convexity that a way to define a convex hull was to take many hyperplanes and like semi-spaces and put semi-spaces as tight as possible around our set, and that would generate the convex hull. So if you imagine drawing line, I'm very bad at drawing lines. Let's try that again. In all directions, and so on, the intersection of all these lines would generate a convex hull around G, right? And if you look, because it's got this like wobbly stuff where the constraints aren't satisfied, the tightest line is not going to get as high as it should. It's going to, it's getting stuck by this, so it's not modeling well just the area around the feasibility set, because we can't differentiate between the feasible and non-feasible points without more information. So if you thought, and I'll show you why this is connected to the dual, but if, let's just start with this idea. Assume you can represent this, and assume you can try to calculate its convex set, and you say, okay, where H is smaller than 0, where does the convex set achieve its minimum? It would be here. Okay? So our algorithm until now is create G. We're not smart enough to only look at this part. We look at all of G. We calculate its convex set, and we take the best feasible point in the convex set instead of G. And you can see that it's guaranteed to be smaller than the optimum all the time, just by construction. And also you can see that if the problem is convex, you have strong duality. Because if the problem is convex, this set G is convex. So let's draw another image of it. So if our original problem was convex, G would be convex. And when you take the convex hull of a convex function, you get the exact same thing. So you would get a plane here, and you would get that the primal solution and the dual, and like the true solution and our solution through convexity are the same. So that's what's going on. And now why is it, why does duality do that? Well, look at what duality is doing. So duality is computing the Lagrangian. So it's doing f of x plus some ui hi of x plus some vj lj of x. And we said we thought of these as just points. So this is just t. This is just h. This is just l. So it's taking this function t plus u transpose, all the h's, plus v transpose all the l's. And this, if we put this equal to something, this would describe a line, right, in a high dimensional space. And when you optimize this, what you're doing, I'm not going to go through all the calculations because you have to think about it a bit on your own, when you're optimizing this, you're pushing the line as high as you can. And where the constraint that u is smaller than equal to 0 comes into play is that it focuses your attention. U is the dimension on this axis, on the h-axis. So lines that have u smaller than 0 are lines that are pointing downwards compared to this axis. So they're lines in this region of the space. So what the dual optimization problem is doing is saying, let's find all the lines that are of negative slope along this axis, push them as high as we can against G, stop where we get stuck, take the t value there, and return the best t value across all these lines. Because you see, for one line you get this, for one line you get this, and when you get to the right line, you get here. So this is like a geometric way to see what's going on in the dual. And to me, it's really cool that it immediately shows you why the Slater conditions hold, which nobody ever proved. OK, so if you want to look in more detail, these are in chapter 5, the chapter on duality from Boyd. And that's all I have. Do you guys have questions?
You could have a u that is sloped this way, but still comes to the minimum point times the g.
Say again, you could have a u that slopes this way and still?
Just like for if you on the right hand side, all the positive g is now bigger than the negative h side. You could have a u that is pointed this way and touches the minimum at there, right? If you don't have the unfeasible g part.
If I don't have the feasible g part, so if this doesn't exist, OK, this part.
Right. So the best line will be, okay, still we have the g.
Yeah, because you would choose the horizontal one if this didn't exist. Yeah. I was slightly hand wavy, but it's very, very rigorously proven here. So, OK? Cool. Thanks so much, guys.